Thanks, Peter. Hey, everyone. So today I'm going to be talking about the DeepSeek-R1 paper, which obviously been causing a lot of chatter on the internet for various reasons, some maybe not so legitimate. And I saw it as a good opportunity to see what the fuss was about. I, rather than going through the paper as I usually do, I kind of also use this as an opportunity to dive into a little bit like some of the things that they talk about in the paper, but which are from previous papers. So I'll go through obviously like the main developments. And I think above all, like DeepSeek R1 is more an innovation in like how to chain together different training stages and showing the effectiveness of like fine tuning on particular data. I think the way they apply reinforcement learning is quite interesting, and the results are quite cool and kind of surprising that maybe it hasn't been as effective before. But so we can go over that. But yeah, so I think I found this image online, and I think it's quite a nice way to look at. This is basically what DeepSeek like R1 paper effectively covers, which is a load of different stages that they use to go from a base language model all the way to language models which are trained to do reasoning. And I guess reasoning would be more like before providing an answer to a question, being forced to think about the question first. So having some kind of sort of forcing the model to come up with some thinking, reasoning tokens before providing an answer to the question. So what I'll cover today, and maybe I'll jump between the paper and this, depending on what we cover, and if people have questions, is first DeepSeek R10, which is kind of the first thing they talk about in the paper and the first model that they trained with reinforcement learning. That will lead me on to covering GRPO, which is an alternative to PPO, which is their reinforcement learning algorithm that they cover in more detail in one of their papers from last year, which is DeepSeek Math, where they trained a model to do mathematical reasoning specifically, and they used GRPO, and I think that's why they introduced it, but I'm not sure. That's where I certainly got a lot of details from it. We'll go into like reasoning-oriented reinforcement learning, and then kind of cover DeepSeek. I wrote DeepSeek R1, which is kind of taking the learnings from DeepSeek R10, but then applying some extra steps on top to get to the model that has become so popular. And then lastly, I'll cover a little bit of the distillation because I think there's some interesting like findings from that. I encourage this to be a discussion as well, so like please feel free to jump in, ask questions as I'm going through. So the first bit of the paper is DeepSeek R10, and basically what they did was they took DeepSeek v3 base, which is their sort of base language model, and said, okay, can we use reinforcement learning to get the model to reason, to force the model to reason, and how does that improve the quality of its responses on some benchmark data sets. Now these data sets are the data sets they use to evaluate are quite like maths and coding heavy, and I think one of the reasons for that, or one of the main reasons for that, is that they're sort of verifiable problems. So there's a very obvious reward in that, like you got the answer right or wrong. And so simply it's like, can we use reinforcement learning to improve the quality of the responses and the accuracy of the responses to this math and coding benchmark? Okay, so I'm going to use this as an opportunity to dive into like the reinforcement learning side of things. So one of the more common ways to do like reinforcement learning with for language models is PPO, which is proximal policy optimization. And there's this kind of nice graph from the DeepSeek math paper, which they published last year, which I found quite useful to dive into PPO. I haven't. I'll hold my hands up and say I'm not an expert in like reinforcement learning at all. I've used this as an opportunity to try to understand a little bit more how it works. But I think PPO and DPO as well were covered in a previous paper club, so might be able to find out on YouTube. Um, so so what we have with PPO is, let's say you have your policy model, which is your language model, and you feed it a question, and it generates an output, right? So you take that output and you do a couple of things. So first, you pass it through like a reward model, which gives you like a reward score for this output given the question, and you have a reference model, and you compute the KL divergence of like the reference model to the policy model, and I think so. Basically, and you do it at a token level, and I think the reason being is that you obviously want to train the policy model to like to improve the reward, but you also don't want it to differentiate too much to stray too far from the like original LLM. So we want to like constrain the updates to be within the realm of like the original model, but like trying to sort of tune it towards giving better and better responses, and responses that get higher reward. Now, that gives you sort of a reward score, but that's not what's used in the directly like in the loss. What we have this other value model, and this value model, what it does is it estimates, as I understand, like a it gives a score to the like sort of expected value of like this state. So it sort of gives you like a yeah, I kind of think of it as like an expected value of like this state that you're in of the world. And you take the reward and this value score and you compute what's called like the advantage. So you kind of get a score of like what's the advantage of like this action that you took compared to like the expected value of this state. And then that's used to update the policy model. And this is effective, but there's a couple of but as you can see here, one of the things is that we have two models effectively that we train. So the first is obviously our policy model, which we're training based on the reward that we got from the action it took. In this case, as an LLM, it's like the answer or the output tokens that it generated for a given question. But we also use the sort of result and this reward to update the value model. So we want to make sure the value model is more accurate in estimating the like true the true value of like the state of the world. And so we're improving both the policy model and the value model as we step through and train these language models through reinforcement learning. And this is the sort of the optimization function or the objective function for PPO. And effectively, there's a couple of components. There's like the ratio. So this computes like this is sort of the difference between like the old policy and the new policy. So obviously you're trying to update the policy model to understand how to take better actions in the environment. And this computes sort of that like that difference between the old policy and the new policy. You have the advantage, which is how much the sort of difference between like the reward from the action you took versus the sort of expected value of the environment. And then what you do is, as we said before, you don't want the sort of part of the like proximal policy optimization is that the proximal part, as I understand it, is that you don't want to stray like too far. And so that's why they have this like clipping function where they take the ratio and they sort of clip it to some like boundary of epsilon. And so you sort of constrain it and you take the min of like these two possible values. And so you're calculating an update or like a kind of update direction, but you're trying to keep it from not being too big of an update. Yes, Arvid first.
I think I have exactly the same question as Dwayne. What's the reward?
Yeah, so the reward model in this case is the actual. Okay, so this is something I was trying to get a good answer for as well, and I think the reward model is also the language model in most cases.
But isn't it sort of circular?
Yeah. So was it Peter?
So when from reading the paper, they have like a pretty heuristic reward that has multiple components, but like in terms of the reasoning part of it, what they do is they have like a rule-based reward. So all of the reasoning tasks that they're training the model on are like verifiable. They're either math or coding. So they actually have like, they take the output and they put it through some kind of unit test to see if it's correct. And if it's correct, you get a reward. And if it's not, then you don't.
Yeah.
It's something along those lines. But they
So
have a couple of other things that they also include as part of the reward.
Yeah, sorry. So I think in the DeepSeek-R1 paper, they create their own like heuristic reward function. I think where I was getting confused was in like RLHF. I think that's the reward model gives you is trained based on like labeled data. I think to give you a score of how good your like answer is, I guess. So it's trained based on like preference data.
I see. Thank you.
And I think it's in like DPO, I think, which frames PPO as like a supervised learning problem, I think, where they use the language model as the reward model, but I'm unclear on the details of that. I think Damien did the paper club on that some time ago. So as I mentioned, like the problem, or I guess con of like PPO, is that you have to train two models at the same time. So you're training the policy model and you're training the value model. Now, I was trying to understand whether the value model is effectively also whether they use like a similar architecture, like if the value model is just as big as the large language model, or whether it's initialized from the large language model. I'm not entirely sure. So if someone knows, I'd love to know. But effectively, you're having to perform updates on two models simultaneously. But this value model, the reason we use it is to compute the advantaged. So it uses this like generalized advantage estimation, which takes the reward and the value score and sort of computes this advantage score. So I guess one of the questions was like, what if we could estimate advantage differently? I guess there's also a question in my head, and I didn't find a response when I was preparing for the paper, of why, like, what happens if you just train on like the reward directly? I suppose you're trying to. I suppose there's some kind of better convergence when you're doing like advantage, when you're using the advantage to train rather than just the reward directly. Yeah, Peter.
I don't know either, but I think in order to calculate the advantage, you have to have multiple trajectories for the same input. Like, so you have to have multiple outputs that you generate for the same input, and you compare them to calculate the advantage. So maybe it's something along the lines of like reducing the variance of your update by having multiple different scores for like different answers.
Yeah. Arvid?
Yeah, I think it's very similar. I think the advantage is just to smooth the the training variables, just because you reduce the variance in situations where you expect a high reward, to see that you're actually doing something worse. It's easier to compare against the benchmark, which is your value function, rather than comparing high value with slightly higher values.
Yeah. Dwayne?
And also it's more sample efficient. By putting one prompt through your model, getting a vast range of answers out, you're extracting more information out of that one prompt in the answers, and being able to feed back, give more training data back to your model in the back prop than you would if you only used one input and one output.
Yeah, so I think this highlights the sort of advantage of what they used in the paper, which is like GRPO, which is group relative policy optimization. So instead of having the value model, you get rid of that, you compute the advantage instead as like, how good is this reward for this output relative to the rewards for all of the other outputs for the same question. So you have, again, you have a question, you feed it into the policy model, but this time what we're going to do is we're going to generate G different outputs. And for each of those, we're going to compute a reward. And then we're going to compute effectively, it's really simple. It's just they just normalize the rewards. They just, they do the Z normalization and feed that straight into the same function. So this looks exactly the same. The only minor difference is that they do the KL divergence of the policy to the reference model here, rather than applying it at the token level before, which I think was part of the advantage of the getting the reward. And then they average over all of the outputs. Sorry, over all of the tokens for all of the outputs for a question. I think it's quite cool. So effectively, they're leveraging. I think they just have like some kind of temperature, which I think they specify in the paper, so they can generate G different outputs, and that gives them sort of samples over like possible distributions of answers, and then you can train on like, out of, let's say, 20 outputs that you created, these 2 or 3 are like much better in that they generated the correct answer and they had a good formatting, and so then keep doing more like that effectively. And so yeah, as I wrote here, if you want to, they explore it further in the DeepSeek math paper. So recommend like looking at that if you want to dive into GRPO a little bit more. But that's like kind of that's the algorithm they used to train DeepSeek-R1 0. So they took their base model, they trained it on reasoning problems which are verifiable. I struggle to find what data set they actually used to train this. I don't think they mention it in the paper as far as I could see, or maybe I missed it. And then they use GRPO with, as Peter mentioned, just a very simple reward system, which is the answer correct? And does the output adhere to having these think tokens and having reasoning within the think tokens? I'm not even sure they like evaluate or do any kind of reward on what's inside the think tokens is like, is your response in this expected format of like thinking an answer? This is the template that they use for prompting. So it's super simple. It just says there's a conversation between user and assistant. User asks the question, assistant solves it. And then you must put your reasoning within the think tokens and then put your answer within these answer tags. It's part of their approach. Yeah. And that's how they train R10. So what are the results? Well, it's pretty cool. They, as the steps increase, so as they train the model, there's a really clear, obviously, improvement of this benchmark AIME, which is, I think, mathematical problems. And the accuracy increases from the pass at 1 from like, what's that, like 15% all the way up to like 70%. So a like drastic improvement in performance with like 8,000 steps of training. The red line is the consistency at 16, which I interpret as if you sample from the model and output 16 times, like how many of those or what proportion of those is correct. And I think they estimate the pass at 1 using the consistency at 16. Yeah.
I think the 16 is where they do majority voting. So they'll get like 16 answers and the majority vote of like what the correct answer is the one they use.
Oh, okay. Yeah. Yeah, that makes sense. That makes sense. That's why it's higher than just the, because sorry, they estimate the pass at 1, I think, by doing 16 outputs and just doing like the average, taking the proportion of those that was correct. But I think that makes sense for the majority voting. Yeah. And so they reach like 01, pretty close or past 01 levels just by doing this like reinforcement learning. And what's also interesting is that the model is learning with it's not rewarded by what's going on in the reasoning process, but the reasoning tokens that it uses, the average like increases as the model's being trained. So it's sort of naturally, there's this like emergent behavior that it uses more and more thinking tokens as it's training, because it's getting probably some correlation between the length of the reasoning and how accurate that final answer is. And they discovered this like aha moment, and I saw people freaking out about this aha moment. I mean, I think it's like kind of cool that the model trains to backtrack or to like reevaluate its reasoning. So it learns to reason about the problem, but then sometimes it'll stop and say, actually, let me revisit this differently, and then come up with a better way to solve the problem. I wonder if that's like, because it's like coming from a base model, and I wonder if there's like stuff in the base model that makes it have this kind of makes it like develops this emergent behavior. I'm not sure. But I think this is such a like, I feel like people have used this to like anthropomorphize this model as well, a little bit. Yeah.
This might be a bit of a silly question, but the red text is not something that the LLM wrote. That's just something that they put in there, right?
No, that's something the LLM wrote.
Oh, really?
Yeah.
Wow. It's kind of fun. It's talking to itself.
Yeah. Which I think, I don't know if people have seen, but there's this like S1 model that I've been seeing. I saw yesterday. I don't know when it came out, but they used the way they like got a good performance on like reasoning is that when the model tried to stop thinking, as in to output the end of the think token, they would just inject weight and then get it to keep generating. So maybe there's something there. Yeah, Dwayne.
I was just going to say that I read that as that it was the humans put the red text in there. If they did not, if it was the model, then I think your suspicion that, I agree with your suspicion that that's from the base model. There must be something in the data set that's going, this kind of in reasoning tasks is saying, wait. Sorry, disagreeing with you.
Yeah, so in the paper, which I've got to open here, it says a particularly intriguing phenomenon observed during the training is the occurrence of an aha moment, which is illustrated in table 3, and this occurs in an intermediate version of the model where it learns to allocate more thinking time to a problem by reevaluating its initial approach. So it, as I read it, is like it learns this behavior in the middle of the RL process.
Yeah, thanks.
Yeah. So DeepSeek-R1 is that simple in the sense that they applied reinforcement learning to the problem of verifiable questions, and then trained it on the reward of like, is this answer correct, and is the format what I told you to make it. Now, there was some drawbacks to R1 so it performed really well when you measure like the accuracy of the final answer, but in the process, the reasoning, well, a couple of things. A, the reasoning was not very human readable, as they say in the paper. So what happened was it would mix languages, and there would be some like unexpected tokens that it uses in the reasoning. And I sort of interpret this as like there's some short circuiting, or like in the process of training with reinforcement learning to generate the correct answer, it sort of finds some shortcuts or uses some tokens to some maybe special tokens to like identify or to mean certain things that are not like human interpretable, or to like represent certain things. So that, and the second problem with R1 is that it's been trained with reinforcement learning on these like STEM problems, but on language problems it then suffers. So there's not like it loses, as I understand it, loses capabilities to answer sort of more regular like non-verifiable questions or language questions, things like that. And that was the motivation for R1, which is, can we take the learnings from DeepSeek R1 but use supervised fine-tuning and these multiple stages to get it not only to be great at reasoning, but also to maintain readability of the reasoning prompts, but also be able to answer sort of non-reasoning problems, or more broadly, like other types of like language problems. So the first thing they did was that they, rather than jumping straight into the reinforcement learning, they used some like a small data set of like chain of thought data to fine tune the model. So they're effectively like taking the base DeepSeek v3. So this is not the instruct model. This is just the base language model. And they fine tune it on some chain of thought data that they collect, which in their paper is thousands. Yeah, Peter?
One thing that when I read this that confused me is they have this section called contributions, and they say that they show how to fine-tune a model for reasoning without supervised fine-tuning, and then here the first step in the process is supervised fine-tuning. So I felt like there was a conflict in that there.
No, I think in R1 they do train a reasoning model without supervised fine-tuning. But obviously then it suffers from other problems. It does great at reasoning. Well, it does great at using reasoning to produce correct answers on like math problems. But yeah. So for R1, they make a few changes. They start with first fine-tuning it on chain of thought data. Yes, I think so. What I understood was that some of that the chain of thought training data that came from R10 was for later in the pipeline, but it might also be this one. Not sure, because I couldn't find good details on what this specific chain of thought data is. But then, yeah, so they fine tune, they do supervised fine tuning on the base model, and on top of that, then they apply the reasoning oriented reinforcement learning, but they also apply a language consistency reward. So on top of the accuracy reward and the format reward that we saw earlier, they also apply a reward on language consistency. And what that means, what I read from the paper, is that they just they make sure that the reasoning, the proportion of like words in that reasoning tokens are like the language that you would expect. And I presume that's sort of dependent on the input problem that they feed, because I think they use both English and Chinese questions. So I guess they check that the reasoning language matches the input question. So that gets you this this model here, which is V3 base with supervised fine tuning and reasoning-oriented reinforcement learning. Now, actually, this is not R1. You might think this is R1, but no. This model is purely trained to then get reasoning data, to then do another step of training to get R1. So this model that we've done fine-tuning on and done reinforcement learning on, they do extensive like sort of annotation, filtering, and sampling to take the best sort of examples of like reasoning and answers from that model. They use some like LLM as a judge, and also I believe do human annotations as well, to basically get a set of 600,000 examples of like questions and reasoning outputs from this model. And that forms this like reasoning data. So these are all maths coding style problems, again, which are like verifiable. They also collect non-reasoning data. So this is other data which is like other kinds of problems, like language problems. And they get this from like some fine-tuning data they use for DeepSeek v3, and also they do some chain of thought prompting to sort of generate some data sets where with specific questions and using chain of thought. So they get about 600K like samples for reasoning data, 200K for non-reasoning data, and that creates this like data set of like problems, both STEM and like language problems, which have reasoning within the outputs. And what they do is they take, so this line goes back up to DeepSeek v3 base. So they take the v3 base model again, start from scratch, and do supervised fine tuning on these 800K samples. And the last thing they do to get DeepSeek-R1 is they do some RLHF, where they do reinforcement learning, where I think they do maintain like the sort of accuracy format rewards for the reasoning problems, and they also apply like a preference like reward, like a RLHF style reward on the non-reasoning data. And that gets DeepSeek-R1. So effectively, like they do a lot of training to get to create this data set, and like this really is like the sort of value, I guess, is being able to, it's interesting because like effectively what they say is like it's better to they train a reasoning model just to generate reasoning data. And I suppose in my head, the question is like, how good is this model? And like, is it just worse than R1 because it hasn't been fine-tuned on this non-reasoning data? How they don't say anything about this model. Like this model is sort of like forgotten and discarded, and it's only used for data curation. But I wonder what the difference between these two is. So then they do a bunch of results, which show that obviously not only is it good at like these reasoning problems, which is like sort of comparable to O1 performance, it also demonstrates really good performance on these kind of English benchmarks, which are more non like math problems, but different types of data sets like this alpaca eval, I think they mentioned is like they pit like models against each other. They mention it here somewhere. They have like quite a bunch of different data sets which measure different things, but show that they manage to maintain the reasoning capabilities while also maintaining like language consistency and like performance on language problems. It'd be cool to if they added DeepSeek-R1 0 again, because I'd love to see if it's like terrible at these things. Because I think that would be cool to show like that they maintain some performance and improve on these other ones. And the last thing they talk about in the paper is distillation. So they explore, they actually explore like they do an experiment where they say, you know, how well would this reinforcement learning work with smaller language models? Oh, sorry. So they take Quen, the 32B model, and they apply the same reinforcement learning processes they did with R1 0, and they also do distillation. So they take this kind of combined SFT data that they generate from the reasoning and non-reasoning data and just do SFT on this like smaller base model. And they compare that, and it's much, you get much better results across the board using distillation rather than applying the same reinforcement learning on the smaller base models. And I guess what that, and actually, if you compare, I don't know what the QWQ is actually. I don't know if that's like a reasoning model, like Quen reasoning model. Yeah.
I think it's gonna be a really poor answer, but it's something along the lines of like the best performing model that they could compare it to that's the same as Quen.
Okay. Yeah. I think it's a reasoning model. I think it's a Quen-based reasoning model. But so interesting, they get like really similar performance doing RL on Quen, but doing distillation is like much better. And I think that probably highlights that there's like a limitation to how small the base language model can be to apply this kind of reinforcement learning to it. Like there might be some kind of threshold where these small models you can't apply the same reinforcement learning training to them and get the same performance. But there's like a lot of power in distillation, right? In having this like super high quality, and I think they spent most of their time on this data set, only 32B, on getting this high quality data set. and then using that to train to fine tune these smaller models. And that's exactly what I'll try. Maybe I'll post the S1 paper somewhere, but like I think that's becoming also like more prominent as well as like distillation. If you have like really high quality data to do distillation on, then that works really well. I mean, it's pretty cool, like getting this kind of performance on these tough math problems with a 32B model is it's pretty insane. And so there's some of these models, I think all of them are on Hugging Face. So you can run them locally and try them out. Yeah, these are, if you want the slides, let me know, because I posted these as like just things that I referenced as I was preparing these slides for the paper, but I found them quite useful. Turns out Hugging Face has a whole like course on reinforcement learning, which I'm considering taking, because my knowledge on reinforcement learning could do with a course, could do with improving. But yeah, that's the paper. I'll get just so everyone can see what was done. But any questions or comments?
That was great, thank you. I didn't quite get all the way through the paper, so really appreciate it.
No worries.
I'm thinking that I agree with the fact that the data that they built is a really key thing. It's a shame we can't get our hands on it and see what's in it. And also, it's quite possible that inadvertently, there's data leakage. When I've started making data sets or creating data or cleaning data, it's too easy to go back to the really good examples that I know, inadvertently that are going to be in the test, or near that they're going to be in the test, or it's very hard to fight that urge. So I don't know what they've done.
First of all, thank you so much for breaking this down. Very good job. It's a very big paper, so it was a lot to cover. I'm wondering, based on I hadn't gone through the last part of this paper. I didn't realize that they basically at the last stages they just fine-tuned on like a very refined SFT dataset. Would this imply? I'm pretty sure, but I may be correct. Would this imply that if you can actually get the reasoning steps from a model like O1 or O3 or whatever, you could theoretically distill down and kind of like get the outputs of their reinforcement learning and make approximately as strong of a model just based on reasoning steps? Or is there something else as well?
Yes. Except I suspect that's why OpenAI don't release their reasoning tokens. You can't access them through the API or through
you can.
GPT.
Yeah.
And I think that's because the distillation on OpenAI generated data is against their terms of service as well. I think they're quite careful about that. But there has been a lot of like controversy. Well, I've seen people like accuse DeepSeek of doing effectively distillation using OpenAI data.
Yeah, I've seen that too. Probably not on the reasoning steps, but more on the.
Yeah, like all of these, like this data set here, for example, like this chain of thought data. It wasn't quite clear to me where that came from. And then all of this SFT data as well, I'm not sure. I mean, here they say they chain of thought prompt their own model. So, but yeah, it's pretty powerful. Yeah.
I have two thoughts. One is last week we were talking to Yarn, who's our academic advisor at NPlan, for anyone who didn't know. And he was telling me about how DeepMind has released a paper. It might be a bit old, where they use a language model to solve Math Olympiad problems. And in order to do it, they have to, like their method, the best one, they have to train the model for like thousands of GPU hours on each test problem to get good answers. And here, the math data sets that they're working with, the results are like 95% accurate. So I'm wondering how hard the math questions are. Like that you would, because here they're just doing, there's no extra work at inference time really to, or at least nothing compared to what they're doing there for the Math Olympiad problems. So yeah, I'm wondering.
The Math Olympiad problems are truly extremely hard. Like they're really, really, really hard. There are questions that you know, someone like someone very versed with maths, professor of maths, doing maths all the time, you know, who will just go, no, 8 hours, 6 hours of attacking it, go, no, I can't solve this. And when you're sitting this exam, you have a limited time that you're doing it. I think it's over 2 days that you do it. So they are brutally hard. It's usually they're touching on new proofs and new maths.
Okay, yeah. Okay, that makes sense that there's such a huge discrepancy in performance, or at least compute versus performance. And the other thing that this is making me think is that, like, after having read this paper, I feel like they've done a lot of great work, but I don't feel that I've seen anything particularly novel here. And so the reaction that we saw in the stock market from this makes me feel that, like, investors in the US are afraid of China, and more than anything else. Like, this is like a reaction to China having LLMs than DeepSeek's innovation. I know that's kind of like off the topic of this paper, but it just made me think that.
Agree a little bit. Also, I'd like to dig into, I haven't seen good sources for the estimates of the training cost on this. And I've heard that there's lots of small innovations throughout it to drop the cost, but I haven't seen the actual details of those yet. And I think it's more those that spooked the financial markets rather than or maybe both. I don't know.
Thanks.
Yeah, you're right. So in the paper, they don't mention like any training costs, but I have a feeling that that comes from like the base model, like the V3, rather than this like reinforcement learning step. But I'm not entirely sure, to be honest.
Interesting. Thank you. I might dig into that a little bit.
Yeah. Yeah, Damien?
Yeah, so I don't know how much of it is speculation versus actual truth, but there's been more commentary about the idea that DeepSeek reported that there was so and so many GPU hours that they've used to obtain the final version of the model, and that's how people extrapolated their sort of dollar cost being a couple of million rather than hundreds of million of dollars. And in terms of the sort of small improvements, I think one of the big ones was that they had limited GPUs. I think they operated on like the H800s as opposed to H100s, which have a different memory bandwidth than the sort of flagship GPUs. And what ended up, these ones. So what they did was they dropped down to like this PTX level, so GPU assembly as opposed to CUDA, which is what everyone else does, to basically address this problem. So their whole training pipeline was built around the idea that they have limited resources, or limited by memory bandwidth, and that's what I presume created the kind of scare factor that they're able to do this with suboptimal, state-of-the-art hardware and still achieve the same results.
If only we all had a team of people who could code in assembly or like GPU assembly code.
Yeah. It's a very odd language. I used to do a little bit of optimization in it during sort of university years, and yeah, it's very odd to work with. Yeah.
Yeah, but I think also misses out. I don't know, this whole GPU hysteria was crazy because, I mean, obviously you need GPUs as well to serve the models, which is like then a whole other cost on top of training. Not to mention how many training runs they did of this. Yeah.
Yeah, everyone forgets about that this is like report of the final training run, not not the thousands of trials before.
Yeah, exactly.
Slightly off-topic question, but they did the two training data sets, 600,000 samples and 200,000 samples. Has anyone seen any justified way for coming up with what split is good that is cheap? Because I mean, one way is just try different splits, right? But you can't do that. So no, okay.
Yeah, no idea.
Yeah.
I haven't, no. I feel like that's still very much like an alchemy side of things from what I've seen.
I wouldn't be surprised though if they just chose an arbitrary number like 1/3 and then it worked.
Yeah,
like
feels right, and they never change it. They just do that. Yeah.
I have a very rookie question, but I'm wondering, considering we don't have the data sets, it's a very extensive paper, but how much of it is reproducible? Like practically, how much of it can people actually? I have seen some reports on people reproducing some of the distillation parts with very small models. Even then, I'm wondering where are they getting the data sets from?
Yeah, so the paper I just posted in the chat actually is quite interesting because they sort of, I don't know, I haven't taken the time to read too much into the paper, but I came across it yesterday, and they approach this problem of like, take a small model, what's like the simplest way that we can get it to like reason pretty well on these kind of like hard math benchmarks. And they found that like 1,000 questions and reasoning traces was like enough to distill a small model to like improving quite a lot the results. So, but they focus on like the curation of the data set, so like making sure it's really high quality and diverse as well. And they also do some funny training process where they like force the model to keep thinking when it tries to stop reasoning. So I think there's a lot to be learned here still.
Is it possible to trick a model into giving some of its training data out? So the thing is, you can get some of it, like 1% or 2%, but you're not going to be able to get the whole lot out, right? Yeah.
Not sure. Like the only thing I could think of that you could do is if you took Common Crawl or something like that,
yeah,
and you fed in segments into the model and you had access to its logits, you could see like what sequences of text it has the highest probability for.
Yes.
And that's probably training data.
And so I could, on one of the distilled data sets, models, you could start doing that with, and you might be able to recover, an approximation of part of the training data, or the distillation training data, that is.
Great. I guess we'll end it there. Good. Thanks everyone for coming, and Gerard, thanks for presenting. Really good presentation, and
thank you.
I think it's great that it led to a discussion as well. So,
Yeah.
Hope everyone has a good weekend.
Thanks everyone.
Thank you, Gerard.
Amazing.
Bye-bye.